We looked at posteriors over latent variable sets given some data. We saw that a true posterior usually is intractable, so it's incomputable, but we can capture the feature of it with a surrogate posterior q. Of course, we have to select the q which is the closest to our posterior, but we can't evaluate this. Therefore, we introduce the ELBO and the different optimization problem. But what is q? Welcome to this video where we will introduce the mean field approach to find q's in variational inference. Hi, welcome to this new video. As said in the intro, we want to find q's, or in other words, families of distributions that we can use in order to fit a surrogate posterior. Here in this introduction, we saw that our intractable posterior has really interesting features, multiple modes, possibly not symmetric and so on. But in this case, a Gaussian might already be a good fit for this parameter. Of course, this is a one-dimensional example, so it's fairly simple, but still it kind of portrays the idea of variational inference once again. But now we are looking at higher dimensional data, so multiple latent variables. And the main idea of the mean field approach is actually extremely simple, because we say that we have a posterior over a latent vector set. So let this be the latent vector. And let it be, for instance, d-dimensional, so that it have d components. And the idea is to subdivide it into independent distributions that are just multiplied with each other. So we have distributions, for instance, going from d0 to capital D minus 1 over qd of set d. So in other words, for instance, if you have latent variables on 3 different parameters, then this would mean that the latent dimensions are independent. So we note this down, the latent dimensions are independent. But of course, we don't have to subdivide our latent vector only into scalars. You can also make subdivision into smaller latent vectors or into smaller chunks. So this could also be just a subdivision into smaller chunks or smaller vectors. And this is the point we want to start. And of course, now it seems a little strange. The question was, what is Q? What is this family of distributions we want to consider? And now we just introduced a subdivision. But this actually allows us to derive a general result on how we can find these smaller QDs. And based on this, if we then apply it to certain scenarios, we will discover distributions again. Of course, there's a little bit of magic involved and also some knowledge, but in the end, it allows us to discover what these QDs actually are. And that's the big point of it. And for the following derivations, we will look at an example of a latent vector from a 3-dimensional space. So let C vector be from the R3. And this then of course means that our Q of Z can be subdivided into a Q0 of Z0 times a Q1 of Z1 times a Q2 of Z2. Then let us recall that the Q of Z that we want to find here is associated with the maximum ELBO. So let us also note this down in the factorization that we have here. So we have that Q of the vector set that is given as Q0 of Z0 times Q1 of Z1 times Q2 of Z2 is found as the arc maximum over all Q0, Q1 and Q2 over the ELBO based on Q. And then also put in the vector here. Then let us recall the ELBO once again. So that is the ELBO or the evidence lower bound. And it is defined as a functional over our surrogate posteriors Q as the expectation over set latent random vectors distributed according to our surrogate posterior over the logarithm of P of Z and the data divided by Q of Z, closing brackets for the logarithm and closing brackets for the expectation. And also recall the big advantage of the ELBO was that we have the joint here. And if we have the directed graphical model of our problem, then we always have access to the joint. So this is a quantity that is computable once we have a certain surrogate. And of course, the expectation can be written in terms of an integration for continuous latent random variables. And then it is the integration over all sets, and that's the shorthand notation for integration over Z0, Z1, Z2, and so on and so forth, over Q of vector set times the logarithm, and then this one here, which was p of set and the data over q of set, then closing brackets, and then d set for the integration of all the set correspondingly. Then let us plug in our factorization into the ELBO. So then the ELBO of q becomes the integration over z0, z1, and z2 of q0 of z0 times q1 of z1 times q2 of z2 times, well, and then we apply the logarithm rules. So we first have the logarithm of the joint. That is the logarithm of p of z and d. Then minus, because we would have the product in the denominator. If we apply the logarithm, then we get a minus, and the product turns into a sum. And we have log q0 of z0 minus log q1 of z1 minus log q2 of z2, and then closing brackets. And then we have to add the differentials, so dz0, dz1, and dz2. Then let us break out the summation in here, which is consisting of the logarithm of the joint minus the sum of the logarithms of our factorized posterior into two contributions, or into two different integrals. And then we have a contribution by this and the differentials, and we have a contribution by this and all the logarithm terms. In order to shorten the notation, I will introduce the following abbreviations. We will have q0 to be defined as q0 of z0. q1 will be just q1 of z1, and I think you get it. q2 will then be q2 of z2, and we will define the joint just as p. And here take care, we are not talking about the posterior. The p is the joint distribution, so the joint over the latent and the observed variables. Based on this, we then get the following two integrals. First, we have the integral over z0, z1, z2, and q0, q1, q2, then times the logarithm of p, then dz0, dz1, and dz2, right? This is just the first integration here. And then we get our logarithms of the surrogate contribution, which will be minus, and then we have integral z0, z1, z2 of q0, q1, logarithm of q0 plus logarithm of q1 plus logarithm of q2, then closing brackets dz0, dz1, and dz2. In the next step, we want to move our q0 in front of the other integrals over all the other contributions that are not q0. So it will be here. We can't, of course, move it in front of the z0 because it is where the integral is taken over. But then we have some sort of like an outer integral and two inner integrals. And we will do the same thing in here. So in essence, this would yield the following. So we have the integration over z0 over q0. And then opening brackets and closing brackets dz0. And then accordingly, we have to rearrange whatever was in here. That was the integration over z1 and z2 over q1, q2 over the logarithm of our joint, then dz0, dz1. Then we have this first integral and then a minus, and then we have the second integral, which will be accordingly the integral over z0 of q0, then the opening and the closing bracket and dz0, and then inside the inner integral will be then over z1 and z2 of q1 and q2 over the logarithm of q0 plus the logarithm of q1 plus the logarithm of q2, and then closing dz1, dz2, and of course I also have this wrong here, this should also be dz1, dz2. In the first, we see that this inner term, which is inside the orange brackets, does not contain q0 anymore. Whereas for the second, we have q0 still in the logarithm, or the logarithm is applying to q0 here. For this, let us subdivide this second integral into two integrals once again. In one integral where we have the log q0, and in one where we only have the log q1 and the log q2. So in essence, this would mean we keep the first integral, which was over z0, then q1, then the double integral z1, z2 of q1, q2 logarithm of the joint, d set 1, d set 2, and then we can also introduce the brackets here one again, and then we have d set 0. That was just the first line. Then we have minus, and we keep the set 0 over q0, and then we have and with the opening and the closing brackets of d set 0, this will be the same. But now we have the contribution by this one here, which will be the integral over set 1, set 2, q1, q2, logarithm of q0, then d set 1, d set 2. And we have the contribution by the second, by d's here. For this, we introduce another outer integral. We have the integral over set 0 of q0, then opening brackets, closing brackets, d set 0. And in here, we again keep the double integral, set 1, set 2, over q1 and q2 of logarithm of q1 plus logarithm of q2, closing brackets, d set 1, d set 2. And then we see that for the inner term, which is the integration over set 1 and set 2, we also have this log q0. And it would just be a multiplicative constant because it does not contain any set 1 or set 2, right? So we can move it outside of this integration and we move it into this one here because, of course, we also can't move it over the very first integral because it still has this q0 in it. But then we are left with the integral over q1, q2, d set 1, d set 2. Additionally, in this case, we also see that we can move the differential all the way to the front here and also just take the integral over q0 alone and don't have the triple integral anymore because the limits of integration of z1 and z2 do not depend on z0. So this will be moved here, and we can make a similar argument down here and also move this up in the front. And if we then also note this down, we get the integral over z0 of q0, then opening, and the double integral z1, z2 of q1, q2, logarithm of the joint. That's nothing that changed in here, then d set 1, d set 2, closing d set 0. Then we have minus, and here we get the integral over z0 of q0 logarithm of q0 d set 0 multiplied with the double integral of z1 times z2 over q1, q2, d set 1, d set 2. And then we have another minus here, and here we will then get the integral over z0 of q0 d z0 multiplied with the double integral of z1 and z2 of q1 times q2 of the logarithm of q1 plus the logarithm of q2, and then d z1 d z2, and then d z1 d z2. And by looking at this, we can identify that this here will just be 1. And this makes, of course, sense because we could also make a similar argument by splitting out the double integral into the product of two integrals. And if you take the integral of q1 over all the z1s, this will be 1 because that's the property of a probability density function. The same argument can be made here. If we integrate q0 over d z0, then this will also be just 1. Then noting down this last simplification, and we have the integral over z0 of q0, then opening brackets of the double integral of z1, z2 of q1, q2 of the logarithm of p d z1, d z2, then closing brackets d z0. And just for your information, of course, you couldn't do this splitting out of the triple integral into the sum of three integrals here because the p depends jointly on all the three latent variables in our latent vector. Then we have the contribution by this term here, which will be minus the integral of z0 of q0 logarithm of q0 d z0. And we have minus and then the double integral from z1, z2 over q1, q2 in brackets logarithm of q1 plus logarithm of q2, then d z1, d z2. And what we see here and also in this term here is that we have an expectation because we have the expectation over the z1 and z2 of the logarithm of p, and here we would have it over the sum of these two. And we will introduce a special notation for the expectation over only a subset of the random variables. And we will introduce the expectation 1, 2 over something as the expectation over a random vector with Z1 and Z2 that is distributed according to Q1 of Z1 times Q2 of Z2, and we apply this expectation to whatever we also apply this expectation over. It's just a shorthand notation for this. Then we can use this abbreviation or this definition in order to find it at two places in our prior derivation, and we find it here. This will be the expectation 1, 2 over the logarithm of our joint. And this will be the expectation 1, 2 over the log Q1 plus the log Q2. Before we note this down, we can also merge these two integrals back together. Recall earlier we kind of split them apart, but now we can merge them back together. They have the same limits and they have the same differential here. So we get Q0 times and then this expectation minus the logarithm of Q0. So in essence, this will be the integral over Z0 of Q0 times and then opening brackets for the expectation 1, 2 over the logarithm of the joint minus the logarithm of Q0, dQ0, and then minus the expectation 1, 2 over the logarithm of Q1 plus the logarithm of Q2. The important finding and the important derivation is that we now have one term where we have the integration over one of the three random variables. So there is only integration, or you could also call it the expectation, over Z0. And then we have something that does not contain Z0 at all. So does not contain Z0. And that's helpful because if we now fix Q1 and Q2, then we have a functional that is only dependent on Q0. So let's call this fix Q1 and Q2. Then our ELBO is given as the summation of a functional over Q0 and a constant term. Then the ELBO over Q is the ELBO over Q0, which then is the integral over Z0 of Q0 times the expectation 2, 3 over the logarithm of the joint. And recall, the joint contains all the latent random variables minus the logarithm of Q0. Then dQ0, and then minus something that's constant, so we can also make it a plus here. That was a long derivation, and we can now plug this back into our optimization problem. So back into optimization, and recall the optimization problem was Q0 star, Q1 star, and Q2 star is the arc maximum over all Q1s, Q2, and also the Q0 surely, over the ELBO of the Q. And if we now fix Q1 and Q2, or in other sense, we make some sort of like iterative optimization updates. So once we fix Q1 and Q2, then we update Q0, then we fix Q0 and Q2, and we update Q1, and so on and so forth, for instance, cyclically, then we can find a general derivation for the Q0. So in our case now, since we fixed, I will write this down once again, we fixed Q1 and Q2 for the moment, then we have that Q0 is the arc maximum over all possible Q0s, so our Q star is this, over the ELBO over Q0, which in our case was just the functional that we have here. Let me also call this a functional, and I will call this I of Q0, because it's a functional, it takes a function and it outputs a scalar. We can just ignore the constant term here and say that that is equal to the arc maximum over all Q0s of our functional over Q0. How do we maximize a functional? We take the functional derivative and set it to 0. So that's what we will be doing. Take functional derivative and set to 0. Of course, just as remark, you should also add the constraint that we of course are looking for distributions. So subject to the constraint that the integral over Z0 of Q0, the Z0 should of course be 1. And that was also a property we used earlier. But we will later on see that this normalization in essence arises quite naturally, so we don't have to consider it here as a constraint optimization problem. Okay, then let's take the functional derivative. So the functional derivative of our functional over Q0 with respect to Q0, and we have to set this to 0. And if we then take a look at our functional we see that it only depends on Q0 itself. So there is no Q0 prime in it. And this means we can use the Euler-Lagrange equation in order to simplify the functional derivative. If you haven't seen this before, then take a look at the video where I derived the Euler-Lagrange equation. Of course, you can also always take the Gateau derivative here and use the standard functional derivative with the Q0 plus epsilon phi, etc. But here, this boils down to the Euler-Lagrange equation into the format that we can just take the derivative of whatever is inside the integral with respect to Q0, and we can just take the partial derivative. And just to give it like a name, I will call this an L. Then we take the derivative of the L with respect to Q0, but just a partial derivative, and set this to 0. Okay, well then let's do this. Look at the functional form, take the partial derivative. So we have to multiply Q0 with both of the components in our summation here. And then for the first, we get the derivative with respect to Q0 is just this expectation 2, 3 over the logarithm of the joint. So we have 0 has to be the expectation 1, 2 over the logarithm of the joint. And of course, I see this should be the expectation 1, 2, not 2, 3. And then we have Q0 times log Q0. Then we have to apply the product rule. First with respect to Q0, then we get minus log Q0. So minus log Q0. And then we have the last, which will be this one with respect to Q0 is 1 over Q0. Then Q0 over Q0 will be a 1. I will note it down anyways. So that will be Q0 over Q0. So in essence, this will be a 1. And then we see we have an equation where Q0 is kind of like standing alone. So we can rearrange for Q0 or for log Q0. And then we get that logarithm of Q0 is the expectation 1, 2 over the logarithm of P and then minus 1. But I think you already see where I'm heading, because Q0 will be a function of Z0. The joint is a function on Z0, Z1, and Z2, and we fix the data so it does not depend on X anymore. And if we take the expectation over Z1 and Z2, this will then be a function over Z0. So this will be our Q0. And in this case, this one will also be just some sort of a constant, and we can ignore it because we will have to find a normalization for Q0 anyways. So in other terms, we know that log Q0 is equal to this, so up to an additive constant, so we can ignore this, of the expectation 1, 2, or in other terms, the expectation over all latent random variables that aren't Z0 over the logarithm of P, and then also be explicit on this, of Z0, Z1, Z2, and the data, and then closing, and this will be on Z0, and that is the main finding of our derivation. So let me also note this down. This depends on Z0, Z1, and Z2. And if we then take the expectation over, then this depends on Z0 only, and then we have our functional form. Let us go back to the original derivations that we did. And the main point, and also probably the big difficulty, was this step here, where we moved Q0 out of the integral, and then we rearranged all the others, and we found some simplifications. And in the end, we reached at a point where we had our functional on Q0, and we had some constant term otherwise. But we could have also done this for Q1, right? And then we would have the functional on Q1 and some constant term here, and we would have fixed Q0 and Q2. And also for Q2. And based on this, we can derive a general result for this mean field approach. So in general, this would be the following equation, with the logarithm of Qj over Zj is the expectation of all i's without j over the logarithm of the joint over the latent set, and the x being fixed to the data. This is also another handy abbreviation here, and you can just read it as all Zi without Zj. And of course this makes sense because we want to update Zj, or the surrogate posterior over Zj. And now think you have more random variables. So think for instance of 7. Then you would take the expectation over 6, and the 7th would still be a functional dependency, and then we update this one. So in summary, once again, you find a direct graphical model, you have some data, fix the data, then you note down the functional form of the log joint. You take the expectation over all the sets without one particular subset of set, without one particular subset of the set random variables. Then you rearrange, you find a functional form of QZ. You also take the exponential, of course, on both sides in order to get rid of this logarithm. Then you find a normalization constant. And then you do it over and over again until you converge. And of course, this was a little crazy derivation. I hope you enjoyed it and it was helpful. If there are any questions left, then please ask in the comment sections. I would be happy to answer them. And as always, if you enjoyed the derivation, then please consider liking and subscribing. I would extremely appreciate this. Here you will now see similar videos, and I hope to see you next time.